Welcome! In this session, we'll tackle an exciting coding challenge, problem number 240, search a 2D matrix 2. We'll explore different approaches to efficiently solve this problem and analyze their complexities. Let's dive in and sharpen our problem-solving skills. In this problem, you are provided with an MX and integer matrix. The key property of this matrix is that each row is sorted in ascending order from left to right, and each column is also sorted in ascending order from top to bottom. Your task is to determine whether a given integer, called target, exists in the matrix. If the target is found, you should return true, otherwise, return false. For a better understanding, let's take a look at some examples. In the first example, the matrix is a 5 by 5 grid, and the target is 5. Your goal is to determine whether this target is present in the matrix. The output for this example is true, because the target value 5 is indeed present in the matrix. Specifically, it is located at position 1, 1 if we use 1-based indexing, or 0, 1 if we use 0-based indexing. This highlights that the matrix allows us to efficiently identify the presence of a target, leveraging its sorted nature. Let's consider another example, the same matrix, but this time the target is 20. Here, you are tasked with determining whether this new target value exists. In this case, the output is false, because the target value 20 is not present in the matrix. Whether explicitly or implicitly, all potential cells in the matrix have been checked, and none contain the target. To further solidify the concept, let's look at one more example. Imagine a smaller matrix with just one row, containing the values, -1, 3. Here, the target is 3. The output for this example is true, as the target value is found at position 0, 1 using 0-based indexing. These examples illustrate how the algorithm efficiently determines the presence of the target in the matrix. Now, let's go over the constraints and edge cases for this problem. First, the dimensions of the matrix are defined such that M represents the number of rows and N represents the number of columns, with 1 equals M, N equals 300. The values in the matrix range from -10⁻9 to 10⁻9, and both rows and columns follow the sorting properties we discussed. The target value also lies within the range of -10⁻9 to 10⁻9. For edge cases, consider scenarios like a matrix with a single row, a matrix with a single column, or even an empty matrix. Additionally, the function should handle cases where the target is outside the range of values in the matrix, ensuring it returns false in such situations. These constraints and edge cases provide the boundaries within which the solution must operate. To begin with, let's consider the brute force approach. The idea here is straightforward. We iterate through every single element in the matrix and compare each value to the target. This can be implemented using two nested loops, one to traverse the rows and another to traverse the columns. While this method is simple and requires no additional memory, it has a significant drawback. Its time complexity is M*n, where M is the number of rows and N is the number of columns. This inefficiency stems from the fact that it doesn't take advantage of the matrix's sorted structure. Next, we have the binary search approach. Since each row is sorted, we can use binary search to check for the target value in every row. This reduces the time complexity for searching within a row to O log n, and since we repeat this for m rows, the overall complexity becomes M** log n. While more efficient than brute force, this method still doesn't utilize the column-wise sorting of the matrix. Finally, we arrive at the optimized approach, which makes full use of the matrix's properties. By starting at the top right corner, we can systematically eliminate portions of the search space. If the current element matches the target, we're done. If it's greater than the target, we move left to decrease the value. If it's smaller, we move down to increase the value, thus narrowing our search range effectively. This optimized strategy works because of the inherent structure of the matrix. Moving left from the top right corner results in smaller values, while moving down results in larger values. This allows us to navigate closer to the target in a methodical way. The implementation is straightforward. We start at the top right corner of the matrix and use a while loop to traverse as long as we remain within the bounds of the matrix. If the current element equals the target, we return true. If the current element is greater than the target, we decrement the column index to move left. If it's smaller, we increment the row index to move down. The process continues until we either find the target or exhaust the search space. This approach has a time complexity of O, m plus n, as we traverse at most m rows and n columns. Additionally, its space complexity is O, 1, because we only use a few variables to track the current position in the matrix. This combination of efficiency and simplicity makes it a highly effective solution. The optimized approach is particularly powerful because it fully utilizes the sorted properties of the matrix. Starting from the top right corner or bottom left corner allows us to eliminate either a row or a column with each step, making the search process highly efficient. Compared to the alternatives, brute force is far too slow at O, m*n, and binary search per row, while better at O, m*log n, still fails to leverage the column-wise sorting. In contrast, the optimized approach achieves the best possible time complexity of O, m plus n, while being intuitive and easy to implement. This strategy avoids the overhead and complexity of binary search while delivering superior performance. The key insight here lies in recognizing how the matrix's properties allow us to systematically reduce the search space. This is what makes the top right or bottom left traversal the optimal solution for this problem. By directly addressing the problem constraints and leveraging the matrix structure, this approach stands out as the best choice for solving the problem efficiently and elegantly. To begin, we need to clearly understand the input and the problem. We are given an mxn matrix, which is essentially a 2D grid of integers, and our goal is to determine whether the target value exists in this matrix. Each element in the matrix can be accessed using its row and column indices. A simple, brute force approach to solve this would involve using two nested loops. The outer loop would iterate through each row, while the inner loop iterates through each column within the current row. For every element matrix, I, j, we compare it with the target. If we find a match, we immediately return true. Otherwise, the search continues. If the loop's complete without finding the target, we return false. It's also important to consider edge cases, such as when the matrix is empty, meaning no rows or columns are present. In such scenarios, we should return false right away, as there's no data to search through. Now, if the matrix is sorted and we know the smallest and largest elements, there's an opportunity to optimize. For instance, if the target is smaller than the smallest value or larger than the largest, we can skip the search entirely. Let's visualize the brute force approach using a simple 3x3 matrix example. Starting at the top left corner, matrix 0, 0, we check if the value 1 matches the target. If not, we move to the next column, matrix 0, 1, and continue row by row until the target is found or all elements are checked. This exhaustive search ensures that every element is considered, so if the target exists, it will be found. However, this approach is inefficient for large matrices because it takes O, m*n, time, where m is the number of rows and n is the number of columns. The algorithm's efficiency can be improved with early termination. As soon as we find the target, we stop further computations, saving valuable processing time. This algorithm is also space efficient, with a space complexity of O, 1. It doesn't use any additional data structures beyond the input matrix, and accessing any element like matrix I, j, takes constant time. The nested loops ensure that each element is visited exactly once, with the outer loop running m times for the rows and the inner loop running n times for the columns. This results in an overall time complexity of O, m*n. Additionally, each comparison between an element and the target takes constant time, so the total number of comparisons is proportional to the size of the matrix. It's also critical to handle edge cases, such as checking for an empty matrix before starting traversal. This prevents errors like accessing invalid indices and ensures the algorithm is robust and reliable. When dealing with sorted matrices, there are optimizations that can make the search significantly faster. For instance, if the matrix is sorted row-wise or both row and column-wise, we can use techniques like binary search or stepwise traversal to eliminate unnecessary comparisons. Another optimization involves pre-filtering the target. If we know the smallest and largest elements in the matrix, we can quickly determine whether the target falls within this range. If not, we can skip the search entirely. Finally, the brute force approach can be expressed in pseudocode. This simple implementation begins by checking if the matrix is empty. If it's not, we iterate over the rows and columns, comparing each element with the target. If a match is found, we return true, otherwise, we return false after all elements have been checked. While straightforward, this approach can be improved with the optimizations discussed for sorted matrices. This implementation solves LeetCode problem 240, search a 2D matrix 2, using an efficient search strategy. The matrix is sorted in a unique way, rows are sorted in ascending order, and columns are also sorted in ascending order. This property allows us to optimize the search process. The algorithm begins at the top right corner of the matrix, row 0, last column. This position is ideal because it allows us to eliminate either a row or a column at each step. Specifically, if the current element is greater than the target, we move left, decrement the column index, because all elements in the current column below are larger. If the current element is smaller than the target, we move down, increment the row index, because all elements in the current row to the left are smaller. The loop continues while the indices remain within valid bounds. If the target is found during traversal, the function immediately returns true. If the loop exits without finding the target, the function returns false, indicating that the target is not in the matrix. The time complexity of this approach is O, m plus n, where m is the number of rows and n is the number of columns. This is because each step either moves one row down or one column left, and the total number of such moves is at most m plus n. The space complexity is O1, since no additional data structures are used. This solution is efficient and leverages the sorted structure of the matrix to minimize unnecessary comparisons, making it well suited for the problem's constraints. This is the Java implementation of LeetCode problem number 240, search a 2D matrix 2. The logic mirrors the Python solution, starting the search at the top right corner of the matrix and moving either left or down based on comparisons with the target. Key differences include Java's type declarations for variables and the use of the int data structure for the matrix. Here, we are tasked with finding the target value, 5, in the given matrix. The search begins at the top right corner, which is the value 11 at position row 0, column 3. Comparing 11 with 5, we see that 11 is greater than 5. This means any value below 11 in this column will also be greater than 5, so we move left to column 2. Now we are at 7. Again, 7 is greater than 5, so we move left again to column 1. Here, we find the value 4, which is less than 5. This indicates that we should look further down the matrix in column 1, so we move to row 1. Now we are at position row 1, column 1 with the value 5. Comparing this with the target, we find an exact match. Therefore, we return true, as the target exists in the matrix. In this example, the target value is 15, which does not exist in the matrix. Again, we start at the top right corner with the value 11 at row 0, column 3. Comparing 11 with 15, we see that 11 is less than 15. This means we should move downward to row 1, as larger values might be found further down in the same column. Now at row 1, column 3, the value is 12. Comparing 12 with 15, we see that 12 is also less than 15, so we move further down to row 2. At row 2, column 3, we find the value 16. This time, 16 is greater than 15, so we proceed to move left to column 2, as smaller values are located in that direction. Now at row 2, column 2, the value is 9. Since 9 is less than 15, we move down again, looking for larger values. At this point, we are at row 3, column 2 with the value 14. Comparing 14 with 15, 14 is still less than 15, so we attempt to move further down. However, moving down would take us to row 4, which exceeds the matrix boundaries. This indicates that the target value is not present in the matrix after exhausting all possibilities. Therefore, we return false. Now, let's consider a third scenario where the target value is located at the bottom right corner of the matrix. The target here is 17. We will follow the same procedure to locate it. Starting at the top right corner, the value is 11 at row 0, column 3. Comparing 11 with 17, we see that 11 is less than 17, so we move down to row 1. Here at row 1, column 3, the value is 12. Again, 12 is less than 17, so we continue moving down to row 2. Now at row 2, column 3, the value is 16, which is still less than 17. Moving down once more, we arrive at row 3, column 3, where the value is 17. Comparing 17 with the target, we find an exact match. This confirms that the target exists in the matrix, so we return true. Here, we analyze the time complexity of the algorithm, which is O, m plus n. This is because the algorithm starts at the top right corner of the matrix and, in each step, compares the current element with the target value. Depending on the comparison, it either moves left by decrementing the column index or moves down by incrementing the row index. Importantly, each step reduces the search space by either a column or a row. Since there are m rows and n columns in the matrix, the maximum number of steps the algorithm can take is m plus n1. This is the sum of the dimensions of the matrix minus 1, as it traverses the matrix diagonally from top right to bottom left. Once the target is found or the indices go out of bounds, the algorithm stops. This explains why the time complexity is linear in terms of the matrix dimensions, O, m plus n. Now, let's consider the space complexity of the algorithm, which is O, 1. This constant space complexity arises because the algorithm doesn't use any additional data structures or memory that scales with the input size. All it requires are a few variables, such as those to store the matrix dimensions and the current indices, which take up a fixed amount of memory. No recursion or auxiliary storage is involved, so the space usage remains constant regardless of the size of the matrix. This makes the algorithm not only time efficient but also memory efficient, as it operates within the constraints of O(1) space complexity. When we compare the brute force approach to the optimized solution, the difference in efficiency becomes clear. The brute force method involves checking every element in the matrix, which results in a time complexity of O(m*n), as all m rows and n columns are traversed. The space complexity for brute force is also O(1), as no extra memory is used. However, the optimized solution takes advantage of the matrix's sorted properties. By starting at the top right corner and strategically eliminating rows or columns based on comparisons, it reduces the time complexity to O(m plus n). This improvement is significant for large matrices, where the brute force approach would require far more computations. Notably, both approaches share the same space complexity of O(1), but the optimized algorithm is far more scalable due to its reduced time complexity. Finally, let's break down the best, average, and worst-case scenarios for the algorithm. In the best case, the target is found immediately at the starting position, the top right corner, which requires only one comparison, making the time complexity O(1). On average, the algorithm explores about half of the maximum possible steps, but the big O notation simplifies this to O(m plus n). In the worst case, the algorithm traverses the entire diagonal from the top right to the bottom left without finding the target, or it determines the target is not in the matrix at all. Even in this scenario, the maximum number of steps is m plus n1, leading to a time complexity of O(m plus n). To formalize this, the algorithm always performs at most m plus n1 steps, as each step moves either left or down. Since constants and lower order terms are ignored in big O notation, we conclude that the time complexity is O(m plus n). This efficient handling of the matrix's sorted structure allows the algorithm to achieve linear time complexity while maintaining constant space usage, making it both robust and scalable. When tackling this problem, there are some common mistakes that can trip you up if you're not careful. First, forgetting to consider edge cases can lead to runtime errors. For example, what happens if the input matrix is empty or contains only a single row or column? To avoid these pitfalls, always validate the input size before diving into the solution. Next, relying on inefficient traversal methods, like brute force, can result in unnecessarily high runtimes, especially for large matrices. Instead, it's important to analyze the problem constraints and choose an optimized algorithm, such as binary search or divide and conquer. Another mistake is mishandling indices, particularly when mapping a 2D matrix onto a 1D array. Remember to carefully calculate row and column indices with formulas like row equals index // n and col equals index %n. Lastly, don't assume the matrix is fully sorted as a whole. The rows and columns are sorted independently, so you need to design your traversal strategies accordingly. Misinterpreting this can lead to incorrect assumptions about how to locate the target efficiently. Now, let's focus on space complexity and some key interview insights for this problem. Ignoring space complexity can be another common pitfall. For example, using extra data structures to store intermediate results might inflate your memory usage unnecessarily. Whenever possible, aim for in-place operations and avoid auxiliary structures unless they're absolutely needed. In an interview setting, it's crucial to clarify assumptions early on. For instance, confirm whether the matrix is sorted row-wise, column-wise, or both, as this will influence whether binary search or another method is appropriate. Be sure to ask about edge cases, such as empty matrices, single row or single column matrices, and duplicate values. Additionally, be prepared to discuss the trade-offs between time and space complexity. For example, you might be asked to choose between faster algorithms, like binary search, and more memory-efficient solutions, like in-place traversal. Finally, always explain your thought process clearly. Walk your interviewer through the problem constraints, justify your approach, and highlight why simpler alternatives like brute force are suboptimal. Let's expand on this problem by looking at related challenges and alternative methodologies. Some related problems include search a 2D matrix, problem 74, search a 2D matrix 2, this problem, kth smallest element in a sorted matrix, problem 378, and leftmost column with at least a 1, problem 1428. These problems share overlapping concepts and can help deepen your understanding of matrix traversal techniques. For alternative approaches, one option is binary search on rows. This works well if each row is sorted independently, offering a time complexity of O(m log n), although it's not the most optimal for fully sorted 2D matrices. Another approach is to flatten the matrix into a 1D array and perform binary search there. This simplifies implementation but comes with a trade-off. It requires O(m*n) additional space to store the flattened version. If the matrix is sorted both row-wise and column-wise, divide and conquer can be a great option. It's efficient with a time complexity of O(m+n), though it's a bit more challenging to implement compared to binary search. Lastly, we have the two-pointer approach, which is particularly well suited for matrices that are sorted row-wise and column-wise. This technique involves starting from one corner of the matrix, typically the top right or bottom left, and using 2 pointers to traverse the matrix strategically based on comparisons with the target value. The beauty of this method lies in its efficiency, achieving a time complexity of O(m+n). However, it does require careful pointer management to ensure that you don't overshoot or revisit elements unnecessarily. This approach is often favored in interview settings because of its balance between simplicity and performance, making it a highly effective tool for solving this class of problems. Great job! You've made it to the end of the session. Today, we explored the brute force method for search a 2D matrix 2 and discussed its complexities. Remember the importance of analyzing edge cases and optimizing your approach. Thanks for joining, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!